Welcome back, guys, to our new topic all about transition metals. So we're going to have to be covering reactions now that are covering the chunk of the periodic table nobody likes to look at. You guys remember this from Gen Chem. You all most likely hated it, but we're going to have to come back to it now. All right? Hopefully it just won't be as bad this time. Now, it's going to involve, again, metals like you've seen, like cobalt, palladium, and these reactions are probably the cooler ones that you guys are going to be learning. And they're extremely useful. They can do a lot of reactions you guys probably think are not possible um, using what you guys have learned so far. And they can be really useful if you're ever stuck in a synthesis question. It can do some really wild stuff. So let's get started. So what do these compounds look like with these transition metals? Right, so I'll draw one out for you guys. We have cobalt over here, this CO group, 4 of them, and this hydrogen. All right, so let's dissect our formula here. We have a metal, and over here are our nonmetals. Now, ligands, you guys probably heard this word before. So when we have these transition metal complexes, we have our metal, and we also have a ligand. All right, a ligand is usually just a non-metal bound to our metal. All right, and there are different types of these guys. We can, we're going to cover them later before we can get into that. And so we're going to have to cover something called oxidation state, which again, you guys have probably heard in Gen Chem. All right, and we're going to have to cover electron counting, valence electrons, all of this stuff, because it's a little bit different when it comes to transition metals. All right, so let's get started. I'm going to draw a compound here, and I'm just going to clear this out. And so it's going to have a metal, like always. So we're going to have palladium in this case. I'm going to just try to expose you guys to a bunch of different metals. And we have our ligands. All right, and so the ligands are a little bit different than what you guys have seen so far in Orgo. Now, some of them will be similar, but some of them will be fairly different. So we have we have 2 ligands so far, and these are both the same, PPH3. All those is a phosphorus with 3 phenyl groups, and a phenyl is essentially just a benzene. And we have chlorine now. So here are our 4 ligands, all right? 2 of them are the same here and the same over there. So whenever we're doing these sort of reactions, it's important to know the valence electrons we're dealing with, the oxidation states. And to do this, we have to look at our ligands. Now, ligands can either be neutral or they can be negative. Now, neutral ligands, you may see them referred to as L-type. All right, just keep that in your back of your head. And negative ligands, you may hear them as X-type. All right, just in case you're ever looking up something online and you see L-type and X-type, this is what they mean. All right, now ligands can either change the oxidation state or they can leave it as it is. So a neutral ligand, right, has 0 charge. It will not change our oxidation state. A negative ligand contributes a -1 charge, and it will affect our oxidation state. All right, so how do we figure this out? So again, if they're ever asking you to figure out valence electrons, oxidation state, you always have to start by looking at the oxidation state. And so how do we figure this out? Here's our trick, or here's really what we just do. What I'm going to do is I'm going to essentially take the bonds connecting to each ligand and I'm going to put it back onto the atom it's connected to in the form of a lone pair. This bond goes to the phosphorus, same with him, and these 2 go on the chlorines. All right, and so we're just going to redraw them. So we have PPH3 with a lone pair now. Same here. And now if you look at the periodic table, phosphorus is on the same column with nitrogen, and you guys know nitrogen has 5 valence electrons. So this phosphorus has 3 bonds to these phenyl groups and a lone pair, meaning its total formal charge is 0, so they're neutral right now. All right. Now the chlorines, when we draw them, the chlorines right now all have 3 lone pairs. now they're going to all get a negative charge because they have a total of 4 lone pairs on them. And we all know they have 7 valence electrons normally, and now they're going to have a negative charge. And so the way we tell if a ligand will change our oxidation state or not is if we do this exactly. We break the bond, put it back on as a lone pair. If the ligand is neutral, like in the case with PPH3, I'm just going to put a 0 here. This means that these guys are the L-type ligand. They don't change their oxidation state. The chlorines, on the other hand, these are negative ligands because you see, well, they have a charge, a negative charge. So we have a total, if we just add that up, we have 2 -1 charges, right? And so that means our total negative ligand charge is -2. So how does this help us? So what we have to do is we have to use this now in terms of the valence electrons of the metal. So if you guys looked at the periodic table, right, and you find palladium. Now palladium is in the 10th column. What that means is that it normally has 10 valence electrons. All right, so I'm going to write here, palladium, normal, 10 valence electrons. All right, and so what you're going to do is the oxidation state. All the oxidation state is if once you find the total negative charge, right? So the PPH3s, they're all 0. They don't change our oxidation state. I'm just going to add the negative numbers. That -2 that I added, my oxidation state is the positive version of this. So -2, oxidation state is now +2. This means what that oxidation state is the amount of electrons that metal has lost. All right. So what do I mean by that? We just said palladium has 10 valence electrons normally, right? I'm going to take 10 valence electrons minus 2. And I'm going to get 8 valence electrons. This number, 8 valence electrons, is what the palladium has when it is combined with these ligands, all 4 of these. That means that in this compound, right, palladium bound to 2 chlorines and 2 PPH3s, it has 8 valence electrons instead of 10. The reason for that is because 2 electrons are donated by this chlorine right here. So palladium has lost 2. So you see this oxidation state is +2. Remember that electrons have negative charges. More specifically, it's a -1 charge. All right? And so these chlorines each have a negative charge. And so instead of the metal contributing those electrons, the chlorines do. And so our our oxidation state tells us how many electrons our metal is lacking. All right? And so you have to keep this idea in mind, that certain ligands can change our oxidation states. And the ligands that change our oxidation state are going to be these anionic, these negatively charged ligands. And so we can use this trick of dissociating those bonds, putting it back as a lone pair to figure out which of our ligands are neutral and which of them are negative. So just to reiterate, if you're ever asked for the oxidation state or the valence electrons of your metal, what you have to do, break the bond, right, of all the ligands and look at the formal charge. Our neutral ligands don't contribute any change in the oxidation state. The only thing they contribute is electrons. When you have negatively charged ligands, they will contribute electrons and they can change the oxidation state. In this case, we have 2 chlorines. Each of them has a -1 charge, meaning a total of -2. The oxidation state is the positive version of that number. So like we said here, we went from -2 and we just changed it to +2. That is our oxidation state. The oxidation state tells us how many electrons our metal is lacking from its normal state. You guys can think of it. So in our case, palladium was used. Look at the periodic table and you'd see it's in the 10th column, which means it has 10 valence electrons normally. but because it has an oxidation state of +2, and remember, electrons are negatively charged. If I had a lot of electrons, I'd be negative. But in this case, because I'm losing these electrons, our oxidation state should be positive because we don't have electrons. Similar to how carbocations work, right? If I take away electrons from a carbon, I get a plus charge. Metals work the same way. So palladium is lacking 2 electrons, so it's going to have 8 valence electrons. Now that's just for palladium. I can count the total number of electrons used in my compound, right? Our total electron count. And the way we do that is we do exactly what we did so far. The first thing you always need to do, oxidation state. That will tell you the metal valence electrons. Then what you do is you just add the metal valence electrons with all the electrons contributed by the ligand. So I'm going to say electrons from ligands. So in this case, I had 8 valence electrons. And now let's look at our ligands. So all of these ligands contributed a lone pair, right? You can see that if I clear this up a bit. Let's look at this chlorine right here. I broke that bond and put it back as a lone pair. So I can do the same exact arrow this way. Then I'm going to do this color, which means it's contributing a lone pair, which is 2 electrons. Same thing for the other chlorine and those 2 PPH3 groups. So that means I'm going to be contributing 2 electrons from here, 2, 2, and 2. That's 2, 4, 6, 8 total. 8 electrons total. We already had 8 valence electrons from our metal, plus 8 electrons from the ligands. Our total electron count is then 16 in our compound. That is how we figure out our total electron count. All right. So just keep that idea in mind. That's how we would handle a question that asks you, what is the total electron count? All right. So essentially, we've covered 3 sort of questions already: oxidation state, the metal valence electrons, and total electron count. Now what we're going to talk about, though, is the type of ligands. So I've shown you a couple examples here, but I'll show you guys some more in terms of what L-type and X-type ligands look like, just so you guys have an idea of some of the ligands you guys can encounter. All right, I don't want you to be caught off guard when you see something. So let's just clear this stuff up. And again, just like with anything in organic chemistry, you want to be able to practice this stuff. So I suggest you make sure you do your workshop, pre-class quizzes especially, old tests. All right, and so we're going to quickly run through a list of things that can be certain ligands that you guys can see, starting with the neutral ones. All right, so what you'd see is going to be a couple of different types of groups that you have not seen normally. All right, so right here, start with one that you've just seen, PR3. All right, and actually let's label these as columns. We have our ligand, charge, and the last column will just cover type electrons contributed. And let's just move this down. All right. So our first ligand, PR3, our R group in the last compound I showed you was pH groups, which is just a phenyl. So if I showed you what that looked like, in case you're a little confused, our phosphorus, a benzene right here, another one, and again, another benzene. Oh. And then we have a lone pair if it's just PR3. All right. And so you guys can also hear that be called a phosphine, in case the professor mentions it and you're a little bit confused on what that is. So that's going to be PR3. Its charge is neutral. And the electrons it contributes are going to be 2 electrons, like just a lone pair. All right. We also have Nr3, same concept, neutral, and 2 electrons. All right. We can, again, keep going. So another one that you guys can see that may not be that common in terms of what you guys have seen so far in organic chemistry is just water, plain water, H2O. That's also going to be neutral. And again, contributes 2 electrons. The majority of what you guys will see are going to be 2 electrons in terms of what they can donate. You can also see a benzene. Benzene. Now, benzene can be bound multiple ways, all right? But which you, oh wait, you know what? Sorry about that. I'm not going to put this one here yet. We can have alkenes. Let's put that instead. All right, alkenes. Alkenes also are going to be neutral, and they're going to be 2 electrons. Now, I left away benzene for a second just because I don't want to get him just yet. It will break the flow of this chart, and you guys will see why in a minute. Another one we can see is carbon monoxide. All right, this one's also a neutral ligand. And again, 2 electrons. Now, our benzene, I'll put that here now. The reason I didn't want to put him where I did when I had him originally is because while he is neutral, he doesn't donate 2 electrons. He donates 6. And this is a special case, so you'll see benzene 2 types, two ways. If you have your metal, the benzene will look like this. Try to draw that better. And the metal will be bound at the center. You usually see it with the circle there. All right. And so the reason it's 6 electrons is because if you think about it, benzene has 3 double bonds, right? 2 electrons, 2 and 2. So 2 times 3 is 6. That's where we get our 6 electrons. And it's bound at the center, so you could think of it as sharing those three double bonds. All right. And so that's how that benzene would look. I don't know why I wrote Me actually. It should just be M for metal. All right. Sorry about that. And so those are pretty much what you'd see as the neutral ligands. All right. And so remember what we call these guys. These are going to be the L type. All right. Just cut that off. Now our X type, these are the ligands that are negative, right? They can change our oxidation state. So what are these going to look like? Well, we have hydrogen. The hydrogen is going to have a negative charge when you dissociate it. So it's going to be negative. But again, still contributes 2 electrons. All right. You can also have, we're going to have our halides, those halogens, right? So we can have something like, I'll write them here. So I can have Cl minus, Br minus, I minus, and F minus. Again, negative. And 2 electrons. Now you can also have an acetate. So acetate looks like this. Just some R group. Our double bond oxygen carbonyl and our O minus. All right. Now, watch out for this guy. He's a little bit tricky. He's going to be negative. But the catch with him is he can be what's called bidentate. What that means is he can bind to the metal at 2 places. Not always, but sometimes. So I just want you guys to watch out for that in case they ever show you that. So if it's just, the way you'd see it is here's our metal, right? You can have your O. And so if this oxygen is bound to it right there, it's exactly how you do it normally, negative and 2 electrons, right? But if the other oxygen is bound to it, let me just reorient it a little bit. So if we had it looking something like this, it's going to be drawn a little bit badly, but you guys get the idea. So if I have that carbonyl oxygen now bound, that's still negative, still only -1 total, right? The fact that the other oxygen is bound doesn't change the fact that it's still -1 and -1 only. It doesn't somehow become -2. But the electrons change. The electrons are going to be now 4. All right, so I'll just make a note here. If bidentate. All right, so just keep that in mind. We can also, and I'll just move this over. We can also have this cyanide group, or cyano, again negative. Oh wait, should put this here. And this will be negative. And it's going to be 2 electrons. All right, so we can keep going. Some of the other ones you guys can see is you guys can have these alkyl groups, right? So you could see RC3, so R3C, negative, again negative, 2 electrons. Another weird one you guys can see, all right, and just watch out for this, is the allyl anion. Now, the ones I'm showing you, this allyl anion is very rare. Not even sure if I've ever seen it being asked, but again, you never know. But I would stick to what you'd see in a lecture, all right? I'm giving you guys a list here, but I would stick very closely to what you see in a lecture or your workshops and pre-class quizzes. That is where everything will be coming from. So the allyl anion, this guy's negative, but it's a similar situation with the benzene. We have 2 electrons here and 2 electrons there. So instead of 2 electrons being donated, it's actually 4. All right. And now another thing you guys will see is benzene. Again, but this time he's a little bit different. And instead of being bound to the center, put it right here, he's not going to be bound. He's going to be bound this way. All right. Now you guys may be thinking, well, why does this change anything, right? Why is he now negative? And in this case, he actually contributes 2 electrons. What's different? Well, let's do a little trick. Break the bond, put it on that carbon. What do we get? Benzene, and now a negative charge on that carbon. Now that lone pair is not resonating with that ring. It's not aromatic. It's not in that pi system. So he's by himself. So that means 1 lone pair, 2 electrons, and well, we see a negative, so he's got to be a negative ligand, X type. All right. So keep that in mind again with the way that this benzene is bound. And the last one I'm going to show you guys is the cyclopentadienyl anion, right? And so it's going to actually draw it over here. Looks like this. All right, and we can bind it a couple of ways. So again, it's similar to the benzene situation. If I bind it at the carbon right here, at this carbon, right, what we're going to get is 2 electrons. So it's going to get 2 electrons. It's negative, so remember we're going to change, our oxidation state will change. So that's if I put the metal this way. All right. I can also bind it at the center, very similar to how we did the benzene up here. And if we did it at the center, what's going to happen is it's going to be still -1, well, negative right here, but it's going to be 6 electrons, all right? So again, very similar to the benzene, okay? And that's it for these lists of ligands. Actually, there is one more I will tell you, I will put, just because I didn't have it here and I realized it. It's alkenes, right? So you guys will see alkenes, something that looks like this. All right, so these are going to be they're going to be neutral, and they're going to contribute 2 electrons. All right. Now again, there may be more. This may not be a complete list. Use what you see in a lecture, your workshops, in class, and the quizzes. pre-class quizzes, those are your guide. All right, so I would look at those if you want the complete list of the ligands you should be familiar with. All right, so hope this helped you guys. In the next video, we're going to be covering the organometallic reactions that you guys learned through the pre-class videos, right? All those 10 reactions. All right, and I'll see you guys in the next video.